Just finished, where is the benzene? Now we're going to ask, what happens to the benzene? So we got up to here with mass calculation, and then we're going to do the next steps of what can happen to our benzene. The first thing we're going to do is biodegradation, and then we'll do advection, dispersion, retardation, and then follow it up with some more notes on breakthrough curves that you'll see as we go here. So back to our conceptual model of the groundwater contamination. We're going to look at the biodegradation, how the absorption affects how fast it goes, and how it spreads out, and understanding that it's being moved along with the groundwater, which we call advection. So we'll look at changes due to dispersion. That's the spreading out. Dispersion spreads out the mass, so it does not change the mass, it just spreads it out, so that lowers the concentration. Concentration mass per volume, it spreads it out over a bigger volume. Adsorption or sorption, this results in retardation. It also does not change the mass of the chemical, but it slows down its transport. So as it goes along, it stops along the way on the solids. And the biodegradation, which actually does reduce the mass of chemical or reduces the amount of benzene, it might be transformed into other things. So biodegradation does actually reduce the mass of the chemical. So we'll start with that. So biodegradation, we're going to assume simple first order kinetics is how we're going to do it. There's more to the story. There's different electron acceptors. We'll talk mostly about oxygen. I'll talk a little bit about other electron acceptors, different environments, complex effects, but we're going to kind of simplify it with the first order kinetics, which is actually the way it's done 99% of the time in remediation sites. What do we mean by reaction kinetics? So a reaction rate is a change per time, or we can write this as dc dt. So this is just math as a language. D is a change in concentration per change in time equals some coefficient times the concentration to an exponent. We can use the same thing for concentration or mass or a number of bugs or something like that. N is the reaction order. So the change in time is proportional to the concentration to the n power. A zero order would say the change in concentration per time is proportional to k times c to the zero, which c to the zero is just 1, or it's just a constant. So a zero order reaction is constant growth. We're almost always dealing with first order reactions, where the rate is directly proportional to the amount we have. So the change in concentration with time equals kc to the 1, or just kc. An example of first order kinetics is for exponential growth. If we say the population increases by 1% per year, then a 100 population leads to a 1 increase per year. 100,000 population leads to 1,000 increase per year. So that's all first order kinetics is that the rate of change is proportional to the number you have. It's not some magic biological process or something like that. But natural processes do often result in first order kinetics. So if I integrate this equation up here, dc dt equals k times c from t of 0 to a t of t, some later time, and c from c0 to c, we get c equals c0 e to the minus kt. Most of the time, well, all the time in this class, but most of the time in our applications, we're talking about exponential decay. So the concentration is going down with time. So we get C equals C0 e to the minus kt. So we can say we have a negative k, but we usually write it like that with the negative in there. Or we could say C0 equals e to the lambda t. So in the applications we're going to use in the homework and most of the literature and guidance documents I see, they use a lambda instead of a k. It's the same exact thing. By the way, I can rearrange this equation. I can solve for the time. It's e to the minus kt, so if you take the log of both sides and rearrange, you get t equals minus the log of c over c0 over k or lambda. So this is our first order kinetic equation, we'll do this thing upside down, backwards and forwards. C equals C0 e to the minus KT, or C over C0, pull the C from the right over to the left. C over C0 equals e to the minus KT. So K, or lambda, we're going to use a lot, is the degradation rate constant. And the units of that are time to the minus 1, or the inverse of time. Day to the minus 1, or year to the minus 1. So we take that coefficient times time, and then we have a unitless number. Exponential decay looks like this. Start at a C0, and then it goes down with time. This is concentration versus time, and it has that exponential decay. So this equation, by the way, is that the C equals a C0 of 50 times e to the minus, and K, or lambda, 0.05 times T. We can also, if I say the K, or the lambda, is 0.05 datus to the minus 1, you have a feel for how fast that is? Not really. So a lot of times we express first order rate coefficients as half-lives. So the half-life is the time it takes to get the concentration from what it starts with to half of that. So if I take my C over C0 equation, equals 1/2 equals e to the minus lambda times, I'll call the half-life there T half. So T half is the half-life. So I can actually solve for, I see a mistake here, but I'll correct it in your notes. K, or lambda, equals minus log to 1/2 over T half. So I can convert back and forth between a half-life and a lambda. So that T half equals minus log of 1/2 over lambda. Minus log of 1/2 is the same as log of 2, and the number is 0.693. Staying with our example here of lambda equals 0.05 days to the minus 1, what is the half-life? Well, the half-life is just minus log of 1/2 over 0.05 days to the minus 1. So that gives you 13.9 days, or about 14 days, about 2 weeks. So that says the concentration reduces by half every 2 weeks. So we start out at 50. After 2 weeks, it's 25. After 4 weeks, it's 12.5. After 6 weeks, it's 6.25, right? And so on. So that gives us a feel for how fast it's going down, in addition to the number itself. So we like to use the half-life. We'll go back and forth with those. You'll see in the software we use, you can put in a half-life, or you can put in the K value. A note also, if you look at that equation, if you take the log of both sides, you find that the concentration, if I plot it on a log scale versus time, you see that's a straight line. Here's an example. We have subsurface contamination. We have to get it down to less than 0.6 milligrams per liter of dimethyl chicken wire, the groundwater. Currently, it's 64. So we're going to install an enhanced biodegradation system to biodegrade the chemical. From our experience, and we can look this up in books, these numbers vary a whole lot. So what we really do is we calibrate it to the site. We find that the half-life of DMCW at the site with enhanced bioremediation that we're going to do is about 2 years. It's very slow, by the way, but the number works out good here. How many years are estimated to reach the goal? What is the estimated concentration after 5 years, assuming this half-life we hear? And what is the first order constant that corresponds with this half-life? So we said that it's at time 0, concentration is 64, and then we have a 2-year half-life. So at 2 years, it's 32. 4 years, it's 16. 6 years, it's 8. And 8 years, it's 4. 12 years, it's 2. How far do we have to go? 0.6. 14 years, it's 1. 16 years, it's 0.5. So it's going to take us somewhere between 14 and 16 years. Well, how can I know that exactly? Again, this is an estimate, but with the numbers here, how do I know this exactly? Well, we said that if we solve this, that C part B, C equals C0 e to the minus KT. We don't have a K, we just have a half-life. A, we said that T equals minus log of C over C0 over K, or I might call it a lambda again. I'm intentionally using these interchangeably, okay? I need the K or the lambda to do that. Well, no law says I can't do part C first, right? So let's do part C. The rate constant, lambda, equals minus log of 1/2, which again is the same as the log of 2, or what, 0.693, something like that, over T half equals, what do we say that was, 0.693 over 2 years. And that equals 0.353465, 0.335, and the units are years to the minus 1. So part A, the time it takes to get to the cleanup level, equals minus log of, it has to get to 0.6 starting at 64 over the lambda of 0.35 years to the minus 1, and that equals 13.5 years. Which means I made a mistake here. But rather than re-record this, I'm sure you caught this. I was just doing it to test you. 8, 10, 12, 14. Sorry about that. So 13.5 years is right in there. And then part B, we said, what is it after 5 years? In part B, C equals C0, 64, up there, e to the minus lambda, 0.35, years to the minus 1. And I like to write the units on this because it's easy to make a mistake and cross up units and get totally messed up. That's 5 years. And that turns out to be 11.3 milligram per liter. So that's between, at year 5, it's between 16 and 8. So 11.3 is right in between there. That's really as much as you need to know for homework and testing and stuff. But a couple more notes on this you might want to put in the back of your head. Oxygen usually works best, not always, not for every contaminant, but biodegradation usually goes fastest under oxygen conditions. We can enhance the oxygen by injecting air in the ground or injecting oxygen-containing materials that break down and give off oxygen in there. There are other alternate electron acceptors other than oxygen. So oxygen is aerobic. The other ones are anaerobic. So if water is approaching the contamination or approaching a food source in general, the oxygen will be used up by the bugs, and then the nitrogen will be used up by different bugs. And once the oxygen and nitrogen is gone, then the sulfate will be used up. And once the sulfate is gone, then the iron will be gone. Then the iron will be used up. And what it does, it uses the iron from the soil, which is an Fe3 plus oxidation state, and it oxidizes it to Fe2 plus, which is soluble. So what you'll see in the groundwater, it hits a contamination site. It starts out, you'll have high oxygen, and then if it has nitrates, they'll drop out, and if it has sulfate, they'll drop out, and then iron will come back in, or manganese. And when we first found out about this years ago, by my colleague and I, we got all excited and we went out to a site and we measured this, and it was perfect. The site did not have nitrate, but oxygen dropped out, still has sulfate dropped out, and then the iron came up. So the first site we did that, it worked perfect. All the other ones after that, it didn't really work perfect, but conceptually, theoretically, that's what's happening. So there is biodegradation when you do not have oxygen. This is a little graphic of it. Leaving the contamination, you're going the other way. In the source zone, there's high contamination, and so the oxygens drop down. And then as the water goes away from that, we start getting some more oxygen back in the water, and we have the reverse of that. So at the end of that, you have the oxygen again, and you have the reverse of this process. So just a couple notes there. In the homework, we're going to use the bioscreen model. All we'll do in the model is we'll enter, we have other stuff to enter in there too, but as far as the biodegradation, we'll enter in the first order decay rate, the lambda. So that's all we'll put in there. You can actually put in information on the other electron acceptors. But we're just going to keep this simple with our lambda. A couple other notes. There are co-substrates where if you give us the bugs, you want the bugs to eat the food, and where the food is the stuff you want to get rid of. Sometimes if you add other stuff in there, a co-substrate, the bugs will eat the food. I say the bugs will eat the burger if they have ketchup. So the objective of this, it's like in a wastewater plant, if you're a civil engineer and you've done environmental engineering, the goal is to keep bug happy. You give them the environment they want, and sometimes you can inject other microbes in there, but it usually works best to just try to make the local bugs happy. So keep bugs happy. All right.